Howdy, everybody. Back to it again. I think we left off here. I know one class we got a little further than another, so I'm just going to refresh your memory. We were looking at this reaction where we had these three reactants, and we were trying to determine the order of reaction for each of them. And I think in first period, we had successfully determined the order according to the bromate, and then we kind of just real quick talked about how to find the order according to the bromide and the hydrogen ion. And then in fourth period, I think we actually got to the end of that and saw our rate law. So our rate law for this is, there's our order according to the bromide, which hopefully first period you can kind of look at that and see how that came about. And then for the hydrogen, same thing. Looking at the data, how we got second order for the hydrogen. And then when we look at the rate law, it looks like this. Although I would have written here rate equals, and then this part of the rate law. Now, one of the things I wanted to make sure I mentioned was sometimes you're asked about what's called the overall order of the rate law. So I'm going to skip back real quick to a couple of slides here that talk about, come on, okay, the overall rate order. And that is just merely right here. So this is back a few slides from where we were. The overall reaction order is what we call the sum of N and M, or the exponents, whatever those orders are. So if you are asked for the overall reaction order, all you have to do is sum up those exponents, and that will be what we call the overall reaction order. So going back to this reaction here that we determined, sorry y'all, let's get there. There we go. The overall order of reaction would be this one here plus this one here plus the two. So that would be overall order would be a fourth order for that. It's a lovely scribble. So that's another question that might be asked periodically. Then, as I mentioned before, after you get the rate law, what usually is coupled with the question is determine the K. What is the rate constant? Again, go back to your data table. You'll be provided a data table. And for this one, we had 4 different experiments. We can pick any one of these experiments. It doesn't matter which one. I always like to pick the one that looks like the numbers are the easiest to work with. And we plug in the concentrations into their respective spot and the rate into the respective spot of that rate law that you just determined. So again, fast forwarding or whatever, here is determining the K. So this was reaction 1 or experiment 1, and we plugged in the corresponding rate. We plugged in the bromate concentration, the bromide, and the hydrogen ion concentration. Make sure you raise them to the appropriate powers that you see there. And then follow through doing your algebra. Make sure you're following with your units. I told you that's very, very important because the K's will have a specific unit and it will vary based on the order of reaction. So once you do your algebra for that, we end up with K as 8.0 liters cubed per mole cubed, which is basically the inverse of molarity cubed times second. So our K value is that. Okay, and again, a lot of times those two things are coupled together. Find the rate law and then the K. Another thing is, I mentioned before, then you might be given a scenario where once you have your rate law and your K, then you may be given different concentrations and they want you to find the rate at those concentrations, or you may know the rate and all of the concentrations except for one, and you have to find that species concentration given that particular rate. Those are the variety of problems that you're typically asked for that. Moving on, we're looking at the integrated rate law. As I mentioned briefly in class, that is basically taking the rate law and doing an integration to it, which is a calculus process. Some of you know about integrations, but you are not going to have to do an integration. You're just know that they're related to each other. Okay. And so here we're looking at another reaction, the decomposition of N2O5. We saw that earlier and we determined that it was first order. Actually, it was in the notes. We didn't cover it in the notes. I kind of skipped over it. But you can go back in your note packet and look at that if you want to reassure yourself that that is actually first order. And here would be the rate law for that first order reaction. So the rate equals K times that concentration to the first power. Now that's our rate law, okay, but we are looking at the integrated rate law here, and so the integrated rate law looks a little bit different. Okay, this here is our integrated rate law. Now, all of you should have at some point done half-lives and first-order reactions in math. I know you have. I can't remember at what level you did that, but I know you've done that. But you've seen maybe a modified form of this equation here. But let's talk about what all these things are. So a first-order integrated rate law has this natural log in it. So you are going to have to do natural logs, or we call them anti-logs, but e to the x, if you will. So let's talk about what all these things are. So this concentration here with the 0 here is basically the original concentration for the reaction. Sometimes it's called naught, and so we would say the natural log of N2O5 naught, or original. This N2O5, and be very careful on this, this concentration is the amount remaining at this particular time. So T is obviously time. But this is not the amount consumed here. This is the amount that remains. So please remember that, because that can get kind of confusing, especially with the wording and some of the problems that you'll be doing. Okay, so let me see if I can write this in. This is original, and then this is the amount remaining. Okay, so keep that in mind. And then T is your time. Could be on any time unit, actually. Most commonly, time will be seconds. And then there's your K, your rate constant. What I do want you to notice is that this is in the form of y equals mx plus b, and that's going to be critical because we are going to be graphing data and looking for straight lines, and that's how we're going to determine what order a reaction is when we're looking at integrated rate laws. So an integrated rate law is looking how concentration and time relate to each other. All right, so what we've got here is we've got this term here is our y value, the negative k is our m, t is our x, and the natural log of the original concentration is b. So what we'll see here in a minute is that when we plot y versus x, so the natural log of the concentration versus time, if we get a straight line when we graph that data, that will tell us that this particular reaction is a first order rate law. Okay, it's a first order reaction. And that's going to be important. So we're going to be looking at 0 order, first order, and second order rate laws with the integrated rate law, and we're going to be graphing the set of data to determine what order it is. Whereas before, when we were looking at the derivative rate law, differential rate law, I guess, that we looked at the change in concentrations versus the change in rate, and we figured out the exponent which related those two things to each other. Here we're actually going to be graphing, so it is going to be imperative that you can graph on your calculator. On Canvas in the module, I have I gotta look, I don't remember what the name of the module is, but it's like graphing with your calculator or something like that. And you can look at the instructions for how to graph on your calculator in case you've forgotten how to do that. And it is going to be imperative on your test, for me anyway, you will have to graph with your calculator to determine what order a reaction is. Now on your AP exam, you won't be graphing because, well, I don't think you'll have time probably to do a graph on your calculator on your AP exam, but you'll definitely will be interpreting graphs and maybe have to decide whether a reaction is first order, second order, or 0 order based on the graph that they provide for you. So just some heads up on what's going on. All right, so, and then all my stuff's in the way there, but hopefully you can read that. So this is just a comparative between the differential rate law. All right, now what this part here is just saying that this is the rate in respect to A, and A must be a reactant because this is negative. Remember we said that to make all rates must be reported as positive, so since that negative is there, this must be a reactant here. And then here is the actual differential rate law. Rate equals K times A. What does that look like in an integrated rate law? Here's a general integrated rate law. Notice we have no specific species placed in here, but when you write your rate laws, you will write the specific species in for A. and nothing else. No other numbers go in here if you're telling what the rate law is for that substance. Then we can do some things with this. Besides proving that it's first order by graphing, you can run an algebra problem with this. Let's say we know the original concentration of A, and we know how much we have remaining. We could figure out how much time is going to pass, provided we know K. We have to have K, and we will find K by looking at the slope of the line, is how that's typically determined. Okay, so again, we could do a variety of things. We might know a particular time, so much time has passed. We know the original concentration. Then we can figure out how much of that particular species remains, how much, and then by doing a subtraction, we can figure out how much decayed. So there's a variety of things that we can do with that. So let's press on and see what we've got here. So some different things. This is looking at how concentration of the species depends on time. That's what an integrated rate law does. Differential rate law is concentration and rate. That's how you can kind of tell the two apart from each other when all you're given is the data table. I already mentioned this, that it's in the form, well, typically it's given in the form of y equals mx plus b. It doesn't have to be. There are other variations, and I'll show you one here in a second. But the thing you must know with the first order reactions, if you plot the natural log of A versus time, so this would be your y, this is your x. If you get a straight line, it is a first order reaction, and to find K, you need to find the slope of the line. In this case, when we plot these things against each other and we get a straight line, the line is going to have a negative slope. So if we want to find K, we need to take the negative of the slope so that we can find what K is. All right, so that's how we can test if something is a first order reaction. I hope some of that made some sense to you. You can replay it if you need to. All right, so then here, as I mentioned before, is the other form that you could find that same equation. So on this previous slide, we had it in the y equals mx plus b form. If you rearrange that, you can get it in this form here. So just that's all we've done is algebraically move this around. Again, our initial concentration over the concentration remaining at whatever time that is, and then there's our K value, again the natural log. So let's see what we can do with this. All right, now you're gonna need your book for this because I do not have the data table provided for you. So yes, you were issued a textbook so that you could actually use it, not just to sit in the bottom of your locker. Here we go. So we're going to do a little chemistry aerobics. Open up your textbook, and we're looking at page 565. If you look at example 12.2, there's a data table there that lists concentrations of N2O5 over a period of time. I don't have it on the slideshow, so hopefully if you've got your book, you can take a look at that. It says here in the problem, verify that this reaction is first order in respect to N2O5, and then they also want you to find the rate constant. Okay, so we've got a graph. That's what we're going to do. We got those integrated rate laws. So first order, remember, is the natural log versus time is what we're going to graph. Well, in the data table, they have given us the concentrations. Now what we're going to have to do is convert those to natural logs. So we're going to take the natural log of all of those numbers, and we're going to plot them versus time. Okay, and then when we do that, if we get a straight line, that verifies that it's a first order. So what we've got here is we've got the data table that's been modified. This is not the original data table in the problem, but here are all the concentrations converted to natural logs and their corresponding times. And then they generated this beautiful graph here for you, and we notice that we have a really nice straight line here. So that's our verification that this is first order when plotting the natural log of that substance versus time. Well, there goes the tornado sirens. They said they were going to run them for a special reason today. So anyway, if we take a look at that straight line, first order reaction. The second question of that problem was determine the K, or the rate constant. So we're going to have to find the slope of this line. So we can look at 2 points on that line, do your rise over run. That was pretty cruddy, but do your rise over run, change in the natural log concentration over the change in time. Now something to keep in mind, the unit here. What would be the unit for the natural log of a concentration? And everybody will say Well, there is none, okay? So there is no unit for a natural log of a concentration. So in our numerator, there's no unit, but in the denominator, we have seconds. So let's see what that looks like, okay? What we've done is we've picked 2 points that lie on the line. We found that this is basically the difference of 2 of the natural log values from this table here. I know they picked this last one and maybe the first one. Is that what they picked? Yeah, looks like they took the first and last points, then they took the difference between those two with no units, notice. And then in the denominator, the corresponding times, final minus initial. And we get this negative 2.772, no unit, over 400 seconds. When you divide that through, here's our slope. And then our unit is s to the negative 1, or 1 over s. Now that is the slope. Now we're looking for k. And slope equals negative k, or k equals negative slope. So our actual k value is 6.93 times 10 to the negative third. All right, so here's that changing of the sign in there. And so here's our k value. Now that we've determined that, then we can run some problems in figuring out, well, if I have a certain time that's passed and I have a certain initial concentration, how much of the reactant would remain for that particular substance. So I don't know if this problem shows that or not, but what? I need that. You can't have that right now. You're going to have to wait. Sorry, bud. Okay, sorry, you guys. Ian wants to steal the book from me because he didn't bring home his own book from school. All right, so looking at this next problem here, we've got page 566. You may need to turn the page here for that. And here we're applying that rate law. It says calculate the concentration of the N2O5 at 150 seconds. So that means 150 seconds have passed and they want to know what the concentration will be. So we're going to apply our K value that we solved for, and then you go back to your original data table. Well, you can do this a couple of ways. You can go to the original data table, which is back on page 655 or 565, and plug in the original concentration that was given there, and that was 0.1 molar. Or you can look at that second data table, which actually had calculated the natural log, and just plug in that natural log value there, which I think was negative 2.303. So there's a couple ways you can do that. I can't remember how it's worked out here. I guess they just went ahead and went back to the original concentration. Then our K was determined via the graph, so that'll get plugged in here. And then we're actually hunting this guy right here. So this is our X value here, lovely X. All right, so it looks like that when you plug all your values in. Notice the units. In this case, we've got to make sure that the time unit that we plugged in here matches the time unit that's in the K value. So let's say this were given in minutes or hours up here. You would have to convert that to the appropriate time unit in that. So in this case, it would have been seconds. No, not a problem in this one because it was given in seconds, but be careful of those units, right? And then it just becomes your little plug and chug equation there. Now, the thing we've got here is this is the natural log of the N2O5, and we don't want the natural log. We want the concentration here. So we're going to have to do what old people call the anti-log, or for you guys, it's your e to the x button. Sorry about that. You press your e to your x button. Hopefully y'all know how to operate that. Each calculator is a little different. And we get that 0.0353 is the anti-log of this. And then notice we really didn't have a unit as we went through here because those units canceled. We didn't have a unit, but you got to keep in mind, what is it I'm solving for? What did they ask me to find? Well, they wanted the concentration. So go ahead and put that in as moles per liter as your concentration. Okay. All right. So this would be the point. Do you have any questions? But I can't do that. So we're going to move on. The other part that's coupled with this first order or any kind of integrated rate law problem is we can determine the half-life of a reaction. And for a first order reaction, the half-life equation looks like this. So here's our T1 half. This just means half-life. We got to talk about what that is in a second. And then here's your equation. In your textbook, they give a derivation for this equation. For those of you that are concerned, well, how did they get that? You can look in your book on these 2 pages here. It'll kind of give you that explanation. And then K is our rate constant. So if we know our rate constant, we can find the half-life. And we can do the other way around. If we know the half-life, let's say they give that to us in a problem, we can find the K. And eventually what can happen is we can link this equation here with the first order rate law, and they work together hand in hand. If we know the half-life, we can find K. We can take that K and plug it back into that integrated rate law and solve a problem. So recognize, please, that those two equations will work together. Okay, focusing on half-life. That's the amount of time it takes for half of the original concentration to disappear or to react. Sometimes they use the word decay, especially if you're talking about like nuclear particles that are radioactive that are going to decay. So sometimes they use that wording. You should have learned about half-life. I know you did in math. I don't know that we talked about it so much in first year chem, but that's what our half-life is. It's the amount of time it takes for half of that concentration to disappear. Now here's a really nice little depiction for you of that same species here. Here we start off at the initial time. We have a 0.1 molar concentration, and it goes down to 0.05, which would be half. And if you look over here to see what time that was, that's 100 seconds. So that's the half-life for the N2O5. It took 100 seconds for half of it to go away. Now if we go from 0.05 down to half of 0.05, that'd be 0.025. Then we go across here, and then that would be half of this concentration. And look, another 100 seconds passed. So 200. And then if we take the 0.025, we divide that in half, was that 0.0129 or whatever that is, 25, 12 and a half basically. Okay, read that across there, and look, another 100 seconds has taken place. So a couple things to note here is the half-life is the amount of time it takes for half of this substance to disappear. And for first-order reactions, the half-life is constant. Notice 100 seconds, another 100 seconds, another 100 seconds. Not all orders have a constant half-life, but first-order reactions have a constant half-life. And all of your nuclear decay reactions where you have particles that are decaying from one form to another, uranium and plutonium and all those radioactive particles, they all have they're all first order reactions, decay reactions. Okay, so I do want to make sure that you all understand that that half-life reaction here, or this half-life equation here, can be coupled with the integrated rate law that you see right here, because with the half-life we can find K, and then we can use K in this equation along with the other appropriate variables and solve for any of these three. So please recognize that. Okay, let's see how we're doing on time here. Really wanted to get to second order. So let's try this just to, maybe I'll go a little bit more. So second order rate laws are, the differential rate law looks as this. This again is telling you that this is a reactant because of the negative sign. The reactant is A. So it's with respect to A. So the rate is K, A to the squared, which is your second order rate law. The integrated rate law would look like this. Looks kind of the same, but yet a little different. This is still in your Y equals mx plus b form. So what I want you to see here is now Y is the inverse of the concentration of A. K is still m. The slope is still m. Still K, excuse me, and then X is still time, and then B, your Y-intercept, is 1 over the original concentration. Okay, so again, with the integrated rate laws, we would be able to prove that this is a second order rate law if the plot of 1 over the concentration of A versus time gives us a straight line. That will verify that that would be a second order rate law. Okay, so it's a little bit different, but yet kind of the same. This A sub naught, again, is your original concentration, and this A here is the amount remaining at that time. So, but we're looking at an inverse relationship instead of a natural log relationship. And just a little refresher for you, doubling the concentration of A quadruples the reaction rate. So that was just a refresher from when we were doing our other rate laws. Okay, so again, to plot, to verify that it's a second order, it's the inverse of the concentration of A versus time will give a straight line. If it is not a straight line, I guess I didn't really address that. If it's not a straight line when you plot those two variables against each other, then it isn't second order. Okay, same with the first order. If when you plot the natural log of the concentration versus time and you do not get a straight line, then it is not first order. So you can kind of verify that. You're going to do lots of graphing, you guys. Then this time, if you do get a straight line, this will actually be a positive slope. So in this case, once you find the slope, that actually is your K value. All right, concentration depends on time. We can use that rate law then to calculate any concentration at a particular time. And we talked about this before, so I don't need to spend much time on that. Okay, the half-life reaction for second order looks a little bit different. Take a look at that. And you'll notice this time we have, in that half-life, we have the concentration of our species in there. In the first order half-life, we did not have the concentration of the species in there. Let me roll back real quick. Where are you? There we go. Yuck, that looks bad. Let's take that off. But anyway, notice there is no concentration in there. So what this half-life is dependent upon is K. All right, so the particular concentration doesn't necessarily have an effect on your half-life. That's why your half-life is constant for your first order reactions. But in the second order reactions, notice we had that concentration of A in there. And so as this concentration changes, your half-life is going to change. Notice where this is in our equation. It's in the denominator. So if we start with a particular concentration, it'll have a particular half-life. As the reaction runs, this concentration is going to decrease, get smaller and smaller and smaller. And as that gets smaller and smaller and smaller, what's going to happen to your half-life? Hopefully you see that it will become bigger, right? With it being an inverse relationship there. So as the reaction proceeds for a second order reaction, the half-life actually gets longer and longer and longer. So that's a different relationship there. Okay, so here we've got an example of what they call a dimer, we've got this molecule here forms basically two of them fused together, if you will, and it forms a dimer, which is just basically double of the original molecule. Okay, and it says, given the data, determine the order. So they're not telling us to verify a particular order, they just want us to figure out what the order is. Then they say find the value of K and the half-life. Okay, so we've got a little bit of work to do here. Again, you're going to need your textbook because I don't have the data table presented on the slideshow. So on page 569, there's a lovely data table for this information. They give you the concentration and the time. And so what you're going to do now is make some graphs, figure out what order it is. So it's not uncommon to try and verify the first order. You try that first, try to graph that first order data and see if it's first order, if you get a straight line. And if it's not first order, then you try the second order values that you need to look for at second order, which would be the inverse of the concentration versus time. And then once you figure out what gives that straight line, then you can find the K value and then determine the half-life. So in this problem, since we've only talked about first order and second order, we haven't talked about zero order, you can determine the order by plotting. So what we would do is take that data table given on page 569, take the concentrations and convert them to natural logs. Find out what those values are, plot them versus time. Now you know you guys are all real handy dandy with your calculators, entering your data into your X and Y columns in your calculator. You don't even have to find the natural log first. You can just put in ln and then put the concentration in, and your calculator will actually calculate that for you, if you understand what I'm talking about anyway. So we're going to plot those two things versus each other. If we get a straight line, then we know that that is a first order reaction. If we get a curved line, then this is not a first order reaction. Okay, that kind of says, no, that's not if we get a curved line. So then you have to try another graph. So then you would go to your 1 over the concentration versus time, which would be trying to verify if it's a second order reaction. So then you go back to your calculator and you plug in 1 over the concentration in that first column versus time, or whichever column you need to put them in, I can't remember. And then you're trying to see if that will yield a straight line. If this yields a straight line, then you've said that that's a second order reaction. If this does not yield a straight line, it's a curved line, then you've got another scenario you have to try, and we won't talk about that yet. All right, so let's take a look here. They've very nicely plotted these graphs for you. So this first one is looking to see if this is first order right here. So this one, they're trying first order, because they did the natural log versus time. And this one here, it's harder to see, they're trying second order because they did the inverse of concentration versus time. And hopefully you see there which one yields a straight line. It's not this one, so it cannot be first order. No. This line here in scenario B gives us a straight line, so that because it's the inverse of concentration, it is second order versus time. And so we verified then that it is second order. Notice the slope of that line is positive, as we said that it would be for a second order if it's a straight line. What you need to do is find the slope of that line, okay, and that will give you your K value. And then once you've done that, found your K value, then you can use the equation to solve things. Okay, what is the concentration remaining at time t, or how much time has passed if you know the different concentrations. So here they're just showing you how they got the slope of the line. Remember the change in the inverse of the concentrations, because those were our y values over t, change in t. Notice the unit here, it's the inverse of molarity, right? And so our units for K is the m to the negative 1, if you will, times second. And there's our K value. Okay, and then they wanted a half-life, so we go back to our corresponding half-life equation. We've seen 2 so far. This is the second order half-life equation. So we want half-life. We solve for K on the previous slide right here by finding the slope of the line. The initial concentration was given in the data table on page 569. Just look at the one that corresponds to time 0. It's 0.01 molar. Plug that in for A. Take a notice of our units. Hopefully for half-life anyway, our units are going to cancel out so that we get a time unit, because this is a time value here, so we should have a time unit here. It could be seconds, hours, minutes, days, years, centuries, what have you. Most of the time it's probably going to be seconds, unless you get really, really, really long half-lives. Then you may be changing it to hours or minutes or years or what have you. Okay. So then it's just saying that the half-life means here 1,630 seconds are required for half of that species to turn into its product. Wow, okay, that's it, you guys. We can't do any more than that. I'm going to put your problem set on Canvas in terms of which problems correspond to these slides that we've talked about. Thank you for being so patient with me, and my daughter didn't come home while I was doing this, so I'm glad she didn't interrupt. All right, you guys have a great night, and you guys really are great. I hope that you're not dying too much from all the work I'm giving you. Okay, take care, everybody.